Hello and welcome, ORTools and MTEX community. Welcome to example 7, parent grain reconstruction using the new variant graph approach and advanced variant analysis in lath martensitic steel. So this example has been recently added, and mostly out of the motivation that in MTEX we introduced a new parent grain reconstruction algorithm, which is called the variant graph approach. I'll leave a link to the research paper in the description. And of course, we want to show you how you can use this new approach also with ORTools. So this example 7 is basically a repetition of most of example 1, so reconstruction of lath martensite, but using this new approach. And I will also introduce some advanced variant analysis features that I will show you later. All these things have been released in ORTools with version 2, so there's been a new release right here. Can't see that. Right here, there's been a new release. And yeah, example 7 can be found right here. So with that, let's get started. I have my code open here and my command window on this side, and I will go through this step by step. So if you've already seen example 1, this might be a bit of a repetition for you, but I want to give people a chance that maybe start up with this to understand what all the functions in the script mean. So I can just put my cursor into the first field up here, and then by doing Ctrl-Shift-Enter, I can run this section. So this basically just initializes the command window, and then I can initialize MTEX. So it starts MTEX and sets some default values for plotting, and then it also sets some default paths on where to find EBSD data and where to save images and so forth. You can change these if you want. Then we're gonna load the data, and in this case we're gonna just load the MTEX dataset martensite. So this is also the one you find in the MTEX kind of documentation on parent grain reconstruction. And as a first step, we're going to compute and filter and smooth the grains. So with Calc grains, we can calculate grains from the EBSD data. And we do this with all the index EBSD data, and we take a threshold angle of 3 degrees. Then we remove all the grains that have less than 3 pixels, and we then from the remaining, we remove all the EBSD data with less than 3 pixel grains, and from the remaining EBSD data we then recalculate those grains at a threshold of 3 degrees. In the end, we can then smooth the grain boundaries. So let's execute this. And here we go. Here are our grains. We have 7,002 grains. The next section will then be rename and recolor faces. This is a little bit optional. You can define some face names that you want to use in your code in this field here. And then if you execute a section, it basically offers you to rename those faces that you have in your EBSD dataset. So here we have iron BCC brackets old, doesn't sound very nice, so we can call it alpha prime. And iron FCC, we can call that gamma. And then you can also choose your favorite colors when you're making face maps for your faces. So here we just use red and green, and that's it. So now in this next section, we actually start with the parent grain reconstruction. So what we do first is that we initialize the parent grain reconstructor with this function here, and we have to supply the EBSD data, the grains that we computed, and optionally we can also give a path to some CIF files. This is the case if we, for example, don't have the face that we want to reconstruct in our dataset, then we can supply the crystallographic information with a CIF file. Then here we define the Kodimov-Sachs orientation relationship by an MTEX kind of predefined misorientation between the parent and the child face, and we assign this as an initial orientation relationship to the parent grain reconstructor. And then we use this calc parent to child method, and what this does is that it iteratively refines the orientation relationship by comparing this initial guess to the microstructure misorientations, and then basically updates the guess each time iteratively until the algorithm converges. When we've done this, we should have a refined orientation relationship that really well describes the misorientations we find in our microstructure. What we then do, we define the Nishiyama-Wasserman orientation relationship, which is also somewhat common in martensitic steels. And then we can use this function here to plot the histogram or distribution on how well the orientation relationship that we refined compares with the misorientations that we find in the microstructure, and compare this with Kodimov-Sachs and Nishiyama-Wasserman. And in the end, we can then plot some information on our orientation relationship. So let's execute this section. So here we now basically have to define what's the parent phase and what's the child phase when we initialize the parent grain reconstructor. So we say parent phase is gamma, austenite, alpha prime is the child phase. And then we see here it's optimizing the parent to child orientation relationship iteratively. So now this has converged. And we're getting the plot that I was talking about. So this is called a disorientation. Disorientation is the term when you have a misorientation between two misorientations. So the orientation relationship in itself is a misorientation because it's a relationship between two orientations. Then at grain boundaries, where we have two grain orientations, we have also misorientations between those grains at the boundary. And then this plot basically shows us the difference between misorientations. So here we see, for example, job P2C, that's the one we've refined, that, let's say, the mean disorientation, so the mean error or deviation from the actual misorientations in the microstructure is around 1 to 1.52 degrees. And if we just, let's say, chose Kodym-Sachs and Nishiyama-Wasserman, we would have these distributions, so quite a larger error. And actually, Nishiyama-Wasserman seems to be a little bit better suited for our microstructure. But you can clearly see that refining the orientation relationship gives us a lot better match with the microstructure. And this is only for child-child grain disorientation, so this means only for martensitic boundaries. And in theory, this is also possible when we have some parent phase retained in the in the microstructure. So if we have some retained austenite, for example, we would then get a second tab with a second plot here. So then we get a lot of information here about the orientation relationship. I'm not going to go into detail here right now. I think I mentioned a lot of these things in the first video on example 1 that you could have a look at. So now we've actually found a good orientation relationship to describe our microstructure. And the next step would then be that we can plot some maps. I'm just going to run this section here, and these are all maps that give you some information on your microstructure, and it's not necessary for the reconstruction process, but you get some insights from it. I'm going to run this and then tell you a little bit about the maps. So this is finished now. So the first function we ran was plot map faces, and that's basically just a face map, which is a little bit boring in this case because we only have martensite. Then the next figure that we produced was this plot map IPF P2C. And this basically just gives us the orientations of the martensitic grains. And what we actually see here is that we have the EBSD precision orientation, so everything's resolved, but we also put the grain boundaries around the EBSD data to kind of show where the grain information lies. So it's kind of a mixed grain EBSD orientation plot. Then the next function was plot map GB C2C, and this shows us the misorientation of the child boundaries. So basically the martensitic boundaries, what's the misorientation in color labels. And what we can see is that most of it is either pretty red or pretty blue. And if you look again at our orientation relationship information, here we can actually see the 24 martensitic variants and what the misorientation between the different variants is with respect to variant 1. We can see that most of these misorientation angles are in the 50s somewhere, and that there's few at 4 and 9 degrees, so that will correspond to blue color and red color. That means everything which is not in the very blue or very red color regime is probably not a martensitic boundary, but a prior austenite grain boundary. And indeed, if you look at those outlines here, the yellow ones and the green ones, you can already kind of see where the prior austenite grain boundaries would be situated. So this gives you a first idea of what the boundaries in your microstructure mean. Then the next one was plot map GB misfit. So this is basically what we saw earlier on the histogram, this kind of disorientation plot, where we showed how well the orientation relationship matches the local misorientation of the grain boundaries. So in this case, we see that we threshold this at 5 degrees, and we see that we have dark red color around some boundaries that really resemble the prior austenite boundaries. So this means here, of course, at the prior austenite grain boundaries, we have a very high disorientation because it doesn't follow the Kudimov-Sachs or our refined orientation relationship. And everything inside the boundaries is pretty much at a low disorientation. So this also gives you an idea where your boundaries are. And interestingly enough, there are some sections, for example, right here, where you can see that there's clearly a prior austenite grain boundary going, but anyway, we have blue disorientation. And this can happen if by coincidence, this misorientation actually matches the orientation relationship. This can happen, and later on I will talk a little bit about how the variant graph actually helps us to not get any problems with this. So the last map I plotted was the GB prop, and that's basically the same map as before, just that we translate this orientation into a orientation relationship. No, I think it's called a here it's called the OR boundary probability map. So basically this probability shows you how likely a boundary belongs to the orientation relationship. So it's a boundary that is part of the martensitic microstructure versus not part of the orientation relationship, for example, as a prior austenite grain boundary. So it's a very similar plot to that. So now we actually go into the reconstruction of the microstructure, and here we have some new functions. So one of them is called Calc variant graph, and we assign some threshold values here. And then we have cluster variant graph, where we have this function include similar. So these values, threshold and tolerance, they're actually values that we already saw in a way in this probability map before. The threshold is the value that tells us, okay, at 2.5 degrees, we basically want to, at 2.5 degrees disorientation, we want to define the 0.5 probability in our probability distribution. And the tolerance is basically the interval in which we then want to go to 1 probability and 0 probability. So basically you can define the distribution for the probability of a boundary misorientation being part of your martensitic microstructure. So, and basically you don't have to change this much, I think, for martensitic microstructures, but you can basically, when you run this plot histogram or misfit, when you run this, you can see where the center of your disorientation distribution is, and then adapt these values if you, for example, have a very high average disorientation to maybe get a better reconstruction result. But anyway, that's what these two parameters mean. There is a way of running the same command with this extra option merge similar, which is right now commented out. And what this function would do is that it actually looks for, okay, we have 24 variants, but maybe there's some variants that are very close to each other, and we can maybe just merge them together in order to have fewer variants to run our analysis on. So fewer variants first sounds quite bad, right? Oh, we lose information. But in the case of martensite and steels is such that we have 24 variants in total, and 2 of those variants are always very close to each other. So reducing the number of variants to 12 is actually does not have a big consequence on kind of finding the prior austenite grains and then reconstructing them, but it can actually save us some computational time, and in this case also memory, because one of the disadvantages of this variant graph approach is that it uses more memory than the normal grain graph approach that we treated in example 1. And therefore, if you have very large data sets, it can be a good idea to run this with the extra command merge similar. So now, why would we at all use the variant graph? I already tried to talk about it briefly before, but the problem with the grain graph is actually that sometimes you have so-called spillovers. That is, if you have an austenite grain and a neighboring austenite grain, it can just by coincidence be that this prior austenite grain boundary matches the misorientation of the orientation relationship, and then the grain graph just basically clusters grains in that other prior austenite grain into its own prior austenite grain, even though those don't belong there. And that's because it only looks at, okay, does this misorientation somehow match the orientation relationship? And it basically just advances node by node into the neighboring austenite grain. If in some cases, if we're in an unlucky situation that two austenite grains are situated in a way that the misorientation matches the orientation relationship. So this gives us problems with actually refining those prior austenite grain boundaries nicely. And the variant graph approach does now not only look at, okay, do we have, let's say, misorientations that match the orientation relationship, but it also looks at, okay, and if it matches, which is the parent variant ID. So this becomes a little bit technical now, and I will maybe keep it simple, but it basically tracks at, okay, all the grains that maybe match this orientation relationship. Okay, that's what the grain graph does. You all match the orientation relationship, but we also need to check that they all match the same parent variant ID, so that they basically also correspond to the same parent orientation. Because for each of those child grains, we also have 24 possible parent orientations. So to make it very short, I know it's a little bit complicated, the variant graph takes not into consideration only that some child grains or martensite grains follow the same orientation relationship in a cluster, but also which parent orientation they belong to. And it has to be the same parent orientation for clustering to happen. So in this case, the spillover cannot happen, and you get a nice refinement of the prior austenite grain boundaries. So this is what is happening with the Calc variant graph. And then we have cluster variant graph, where the actual clustering is happening. And this includes similar here. It just shows that if we use this merge similar, that also similar variants share their probability. So this is a command that you can basically keep activated all the time, and it will work with either of those two. So then we do the clustering, and after the clustering, we can see the probabilities of the grains, and then we can actually calculate the parent grains from that. Let me run this section. So now we've gotten this probability map, and we go from 0 to 1 in probability. And what this shows is one probability is just that it's very certain about the assignment of that grain to the parent to a parent grain. And blue or greenish grains just have a lower probability of having been assigned to the right parent grain. So if this is all blue and green for you, then your reconstruction was not very good. Just to say it simple. And this is then these are actually then the reconstructed grains. I mean, we still have the martensitic grains, but from their outlines, but we already have basically computed the austenite orientations of the prior austenite grains. So you can clearly see the outlines here, and you can see an annealing twin around here. Yeah, so this is how the reconstruction works. It's very similar to the grain graph, really, just some different things are happening underneath the hood. Now we can remove some badly reconstructed clusters, and how we can do that is that we can use this command drop calc gb votes and then p2c reconsider all. And this basically means that if we still have some child grains left in here, and there are some white some white areas that have not been reconstructed, it then compares basically with its misorientation with the surrounded reconstructed grains to see if it can maybe find a match and reconstruct those last grains. And if we run this, then we have calc parent from vote, where it actually calculates the orientation from the grain boundary vote. And then we plot the orientation result in the end. And then we see that the entire map has been reconstructed. So now we can do some cleaning afterwards. So we can merge some similar orientations. So here we say everything within a threshold of 7.5 degrees should be merged. Then we can merge inclusions. So some smaller grains maybe that obviously have been wrongly reconstructed can be basically merged. into the larger grains. And then in the end, we can just plot another figure with the final reconstructed orientation map that we have here. So now all these martensitic boundaries from before have been removed and small inclusions have been merged. And from here we can basically do even more, let's say, smoothing and all these things, reconstruct or recompute the EBSD data of the parent grains. For this I would refer to the example 1 video. So now we come to the new part of variant analysis. We had some basic variant analysis in the already previous version of MTEX and ORTools, but now we have actually refined this a little bit. And these are very much, let's say, applications towards specific microstructures, so martensitic microstructures and steels. And that's also the reason why these things are not like generally included in MTEX, which is more of a general purpose tool. So what are we doing here? The first thing we do is just plot the variants and a pole figure. So here we can actually see the variants of our orientation relationship, and we can clearly see that some of them are quite close to each other. And then we can calculate the variant IDs. So now knowing the parent orientation and the child orientation, it can then figure out, okay, what orientation variants of the martensitic microstructure do we find, and then we can plot those. So with this command grains in here, we then plot this on a grain level. So here the thick black outlines, these are the prior austenite grains, and then inside we have the martensitic grains with their variant ID. What we also can do is plot the whole thing on EBSD level. So if we don't use this extra term grains, we actually get the EBSD data index on the variant level, and we can see that we get a lot more refinement within the grains. We'll go a little bit more into detail now what this actually means. So one of the new features that we implemented in ORTools is this compute variant grains. The name is a little bit misleading, but we couldn't think of any better name. What it means is that initially we just calculated the child grains, so the martensitic grains, based on this 3-degree threshold, right? With this Calc grains command right here. And there we just look at the misorientation, of small clusters with each other. What we can do now, after we've actually reconstructed our whole data set, now we know the parent orientation, we also know the child orientation of each EBSD pixel, and then we can see, okay, from those 24 variants that belong to our orientation relationship, how well does each pixel fit to which variant. That's actually how we got this map. So this one is refined a lot further than just the grain level. If we have a look, for example, here, you can see that there's a lot of small pixels actually that are a lot finer than what we initially indexed on as the grain level. So what we can do now is we can actually recompute the grains in MTEX, but not based on the misorientation between the EBSD pixels, but based on their variant ID. And we can do this with this command. And then what we get returned is something called variant grains. So this is basically just a normal grains object in MTEX, but resolved to the variant level. So we're going to get a lot more than 7002 grains back from this calculation. And also we get a new EBSD data set back, which has the grain IDs to that, if you want to use that. So now you can see we have 16,715 grains compared to 7,000 because we have a lot more refinement on the variant level. And we can just have a look how does it looks optically. So we can plot the old grains. So what we initially basically index as grains, that looks like this. And we can also plot the orientations of those new variant indexed grains. We can see that, of course, the orientations are generally the same, but this one is a lot more refined, and you might even say it's messy, but it's it has some merit, as we will see in a short while. So here, for example, we have one big green grain, and here we have like a darker and a lighter green grain. So there's some smaller orientations which now can actually be detected on the grain level. So once we've computed this, we can run this new function called plot map variant pairs. And what this allows us now to do is we can now analyze actually the pairing of different variants. Before it was not really possible because a lot of the variants were basically not being resolved by this normal grain indexing. But now that we have variant precision grain indexing, we can now look at the relationship between those variants. So which variant pairs with which variant. And in martensitic microstructures, this is defined by the different blocks. So here we look at variant 1 to variant 6, and you might know that from all the 24 variants we have in the Kolmos-Sachs relationship, we have 4 different packets, and we now basically took all the variants from packet 2, 3, and 4 and projected them on packet 1. So we only have indexing variant 1 to variant 6, and then we see which variant pairs with which one. So we have variant 1, variant 2 pairing, variant 1, variant 3, and variant 5 pairing, variant 1, variant 6 pairing, and variant 1, variant 4 pairing. And we can color code this in our microstructure. The same can also be applied to a certain parent grain ID. So if you have some parent grain that you want to look at, and just to show you, you can figure out the ID by doing job.grains. So plot job.grains. And then, for example, you want to look at this grain here. You can click it and then you get the grain ID back. And yeah, this is also the grain we're going to look at now. So it's 279. Yeah, so we now get the same information just on the individual prior austenite grain level, which is quite useful, I think. Did I close the previous one? Maybe. No, it's right there. So in this map here, we also have different tabs. So actually we also get a tab here that's a relative block boundary frequency. So it's basically a histogram showing us how frequent is each block boundary type on the entire map level. And also the block boundary density. So how many micrometer of block boundary do we have per square micrometer? These are pretty similar, but not exactly the same. Yeah, that's for basically block boundary analysis. And just to give you a little bit of background, the type of block boundary in your material can indicate whether you have more of a, for example, banitic or more of a lath martensitic microstructure. It can tell you about the strength of your material. So there's many, let's say, parameters you can derive from this, which you could look up yourself. Also, if you enter this function, you will get a reference to a paper from Morito et al. Who've basically been using this method and also show a little bit on how you can apply it. So you can get some background information there. So now we can also do another thing, calculate the martensite block width. This is a feature that has been contributed by our colleague Tuomo Nysonen, and let me maybe just run it to show you what it does. So how this one works is that for a certain parent grain, it basically goes into each of the blocks, which is the child grains, and then looks for the 111 austenite or 011 martensite trace that is closest to the trace of the grain. So basically looks for the habit plane trace, and then it takes the normal vector of this, it's the green one, and then it projects all the points of the grain boundaries onto this normal vector. And in the end, it takes the mean value of all those projections to figure out what's the dimension in this direction perpendicular to the habit plane trace. And then let's say the mean block width is then actually given by the length of these blue lines. So you can get kind of a visual idea of if this makes sense. And it's of course only an approximation because we're working with 2D data and it's difficult to determine the block width this way, but it's maybe a good, let's say it's a good approximation, and you can also, let's say, have very good relative comparisons between different data sets. And here you then have a color scale of the actual width of the different blocks. What you also get on top of that is a histogram of the block width, so you get the relative frequency again. And again, you can also run this for the entire map. When we do that, it takes actually a little bit of time to compute this. So for a large data set, you have to consider yourself if you want to do it or not. And the plot in the end, it will not show you all the traces because it would be impossible to plot all this. But it will show you kind of the distribution of the block widths in your data set, and it will also give you the histogram. So you will get a lot better statistics than just for looking at one grain. So now the computation is finished and we get this map where we get indication of the block width distribution in our microstructure. We maybe just enlarge this. Looks like this. And we then get also the block width distribution. And you can see now we actually get quite interesting, I think, yeah, quite interesting distribution, which probably has some good statistical values or meaning behind it. And we could say that the average block width is around a micron in this case. So yeah, this is one of the newly implemented features. And now we gonna go into the more interactive features. So we have this this function plot stack. I think it's already existed in the previous examples, where we can also just place a parent ID for a parent grain and then plot a lot of different information for a grain. So this is now all organized in different tabs here, and I'm gonna go through each plot to tell you a little bit what we're seeing and how you can use these plots. So these are a lot of plots. Let's start with figure 11. So that's just a parent face, or basically just a face map. Then number 12, that's the child face map. 13, that's the parent inverse pole figure. So this is actually orientation, not face coloring here. Then we have the child grain inverse pole figure, where we get this information, and as you can see, it's all on EBSD level, but superimposed with the grain boundaries of the martensitic variants of the martensitic grains. These are the variant IDs for a grain, also given on EBSD precision. The packet IDs, which mostly makes sense if you look at martensitic microstructures, otherwise you should skip this one. Then the parent grain orientation on a pole figure. Then the ideal variants, the ideal variant orientations on a pole figure, and the ideal packet colored, let's say, orientations on the pole figure. This one is the mean parent grain orientation. Then we have the actual orientations of the child grains colored by variants, colored by packets. And then we have coloring of the variants on an inverse pole figure instead of a pole figure. The same thing for the parent coloring, for the packet coloring. And then we also have the relative frequency of the different variants, so we can again see how much of the grain is has transformed to which variant, and the same for the packet IDs. So a bunch of information basically on a transformed grain. And here we basically specified this by the parent grain ID, and we can also do the same thing on the grain level instead of the EBSD level. You saw that we had all the EBSD data basically on that precision. By using this extra attribute grains, we can get this on a grain level precision. We can also use the addition no frame, which I can show you in a second what that means. And we can also do no scale bar, as we see down here, which I don't have activated right now. So now we're on the grain level. So this is the parent face map, child face map, then the parent mean parent orientation, child orientation, and so forth. You get the idea, right? These are now all grain information, so we only have one orientation per grain. And this attribute no frame actually means that the frame around the plot has gone, which might be nice if you want to use this for a publication. You can also use no scale bar to get rid of the scale bar as well. So this is basically the same information you get just on a grain level. Then you can use this function here to save your images. I'm not going to execute it now, but then you can specify in there in a folder in which you want to save the figures, and it will then basically save all of them nicely in a PNG format. So at last I want to show you this function grain click, and we can now use this in conjunction with very many different modes. So the normal one is just without any extra attribute. I mean, we have no scale bar here and no frame, but you could also run it without those. And what this does, I'm just going to briefly show you. It actually runs this plot stack kind of function that you saw earlier, but in interactive mode. So you can go and click on a grain that you want to look at, for example, this grain, and then it will give you all the information about this grain. And once it's finished with plotting all these things, it will return to this parent grain overview map, and you can click on a different grain. So in this way, you can explore your microstructure, the variants that you have, the packets, histogram distributions, and all these things. So while this thing is plotting, we can look at the next one already. We can do the same thing in grain, on grain standard, as I said before. But we can also use this to look at the variant pairing. So that's what we did earlier, just in an interactive way. So we can run this variant pairs option in grain click. And then we get information on the variant pairing in this grain. So now we got this, and we automatically return back to the overview, and we can look at our results and then just go for a different grain afterwards and continue our analysis as long as we want. Right, you get the idea. And the same thing, the block width measurement, we can do this with grain click interaction. And then there's a last one, parent twins. Maybe I'll show you this one as well as a last thing. As I showed you earlier, we have a lot of orientations that are very close to each other, and on the grain kind of level, it's very easy to oversee those. So with this kind of variant precision grain refinement, we can already get a little bit closer to actually looking at the different variants on EBSD level. And we also have this function parent twins, where it actually looks on the EBSD level whether there's actually any twins, annealing twins hidden in our grains that we reconstructed. This still remains one of the biggest challenges in this kind of parent grain reconstruction for martensitic microstructures. And with this feature, we can basically then refine the reconstruction on DBSD level for individual grains to look for some annealing twins. So I just clicked on this grain down here, and now runs the analysis. And what I figured out actually is that the grain below here, all the way down there, was related by a twin orientation. So even though this was the prior austenite grain before, it actually now took in further sections that are twin related and said, okay, these are actually all one grain with its twin. And then it applies EBSD level orientation precision to then look at, okay, can we further refine the reconstructed result by looking at each pixel of martensitic orientation, how well does it fit to the orientation relationship, and what would be the best parent orientation. And we can then actually see that we have those longitudinal features here that are very likely annealing twins. And we can actually see that on the grain level, it got partially actually recognized during reconstruction, but not fully recognized. And here, if we then look at EBSD level, we can see that this one is, that this is a full annealing twin actually intersecting the entire grain. And yeah, you can then return back to this screen, go to other grains, check those. And either you'll find a annealing twin or you will get some kind of update that there was no twin in your microstructure. This does not look too promising. I mean, there might be some twin relationship up here, but likely not. Let's maybe look at one last one. And it says here no twins in the parent phase detected. So you can basically look through different parent grains and see if there are any annealing twins hidden there. All right, I think I've talked long enough. That's it for now. I will leave some references to where you find the code and where you find the papers and these things in the description. I hope you like this tutorial on the new variant graph approach and the new example in ORTools. And yeah, I'm happy to about any feedback you want to give me, or if you find any bugs, just report them to us. And yeah, have fun with the code.